Okay. Hi, can everyone see my screen? Yes, no, maybe so.
Yeah, we can.
Okay, awesome. And then, and you're still seeing the screen. Cool. Okay, so today we're going to be talking carbocation stability, alkene stability, and then Ashley's going to take over with acid and base stability and boiling points. Can you see this? Okay, awesome. Cool. So to kind of start off with our learning objectives, we're going to first move into alkene stability and kind of think about how can we rank alkenes in terms of what we've seen in reactions. And then we'll move on to carbocation stability and kind of how do we rank carbocations to know what's going to be the most preferred carbocation in a reaction. Cool. So here are three different alkenes, right? And we have these heats of formation right along the sides. So can someone kind of tell me what the general trend that they're seeing in these heats of formation? And the number of attached alkyl groups.
As you add more groups, the heat of formation gets smaller.
Yeah, exactly. And so what is that kind of telling us about stability? So by adding more groups, our heat of formation is decreasing. The more stable the molecule is, right? The lower the. So let's kind of think about why this is. And so, like we said, right, stability is going to increase with increasing numbers of alkyl groups. So to kind of think about why this is, we're going to take it back to Gen Chem. And despite how terrifying this looks right now, we're going to break it down to kind of make it more digestible. So right now we have this sp3, sp2, and sp, right? And what are hybridized orbitals? They're essentially just this mix of the s orbitals and the p orbitals. And hybridized orbitals are essentially just how we form bonds between atoms. And if you'll remember back to Gen Chem, right, our p orbitals are going to be higher in energy than s orbitals. And if we look at sp3 hybridized orbitals, that means you have one s orbital and three p orbitals, right? So you're essentially going to have 25% s character all the way down to sp, which is going to be one s, right? One p, which means you're going to have 50% s character. And if you notice the energy differences, right, the more s character you have, the more your s percentage increases, the lower in energy the bonds are going to be, and the lower in energy that molecule is going to be. And so let's see how that's going to relate to kind of how this idea of how adding more alkyl groups increases our stability. And so in thinking about that, what we've noticed is that increasing numbers of CSP2 and CSP3 bonds leads to increased stability. And so let's kind of break that down a bit more. Can someone tell me what the hybridization of this carbon right here is? Anyone?
sp2?
Yeah, exactly. What about this one? It's sp something. Yeah.
sp3?
Yeah, exactly. And then this one and these two are also going to be sp3, right? And down here, we're going to have that same kind of trend where we have this is sp2, and this is sp3, and this is going to be sp3. And so when we think about the bonds, right, this is going to be a CSP2 to CSP3, which just means we have a carbon that's sp2 hybridized bonded to a carbon that's sp3 hybridized, right? And then if we look at this bond, for example, we're going to have CSP3s. right? And that's going to be the same exact trend for this bottom molecule. And so let's kind of bridge together kind of all of these ideas that we've already talked about. This idea that having more S character is going to make you more stable. And this idea of how by adding more alkyl groups, what you're doing is you're increasing the number of these CsP2, CsP3 bonds, right? Because in this molecule down here, we now have two CsP2, CsP3 bonds compared to this top one where we only have one. And we know that the more S character we have, the more stable a molecule is going to be. And so to bring it back to this statement that the increasing number of CsP2, CsP3 bonds leads to increased stability, right? The more S character we have, the more stable your molecule is going to be. And so that's kind of just the general idea we're going to follow on alkenes. The more alkyl groups we have, the more S character we're able to have in the molecule because we're adding more percent S character. And so let's kind of just put all these ideas together and think about the general order of stability. And so this one, this first structure, is only going to have one alkyl group, so it's going to be the least stable. This is two alkyl groups. This is three alkyl groups, right? 1, 2, 3. This is four. This is also three alkyl groups. And then this is going to be four alkyl groups. And one thing that we're going to notice is specifically paying attention to this structure, which is going to be two alkyl groups. There's actually going to be a difference depending on where you're putting your alkyl groups. And that difference happens to be because of steric hindrances. So kind of thinking back to Newman projections, right? When you're putting bulky groups right next to each other, it's going to make them less favorable. They're not going to like that as much. And so by putting this conformation right here, and a cis conformation versus trans, we're essentially increasing the energy when we're in cis and decreasing the energy, making it more stable when we're trans. Are there any questions so far? Okay. And I guess another thing to point out is that although both of these are three, the kind of main difference happens to do with the arrangement of those alkyl groups. And this is just a general trend you'll need to remember for later on. Okay, so let's kind of do practice problems that go over this. So within this first kind of row, can someone tell me which structure is going to be more stable and which one's going to be less stable using the ideas that we've gone through so far?
Is the one on the left more stable?
And tell me why.
Because it has one alkyl group, whereas the other one has no alkyl group.
So I agree that the one on the left is more stable. And to just refine your explanation a bit, right? If we look at the number of alkyl group attachments, right? We're going to have 3 here versus 2 here. So the reason why we're more stable in this structure is because we have more alkyl groups attached to that double bond. Does that make sense?
Yes.
Okay, awesome. Okay, what about in the second row? Which structure is more stable and which one's less stable?
The one on the right would be more stable.
And why?
Because it's trans as opposed to cis on the left.
Yeah, exactly. Perfect. We're essentially decreasing the steric interactions that you would have between these groups when we put them in trans. Cool. What questions are there on these two practice problems? This is going to be a super important topic that comes up a lot when you're thinking about reactions and like which alkene is more stable and which one would be the preferred product. Okay. Sweet. So now that we've gotten through alkene stability, let's think about carbocation stability. And so as just a general rule, this is going to be the trend that we're going to be following. So primary carbocations are going to be the least stable, and tertiary carbocations are going to be the most stable. And kind of to look over where we're getting, this primary, secondary, and tertiary notation, what that means is when we look at the carbon that has that plus charge, right, the carbocation, we're thinking about how many alkyl groups, how many R groups is it attached to. And so in the primary carbocation, right, that carbon with the plus charge is only attached to one other carbon-based group. And a secondary carbocation, the carbon with that plus charge is attached to two carbon-based groups. And in the tertiary carbocation, that carbon is attached to three carbon-based groups. And this is, obviously the maximum number of, groups you can be attached to with your carbocation. Okay, so now let's kind of think about why this matters. And to kind of go into that, the first thing we're going to look at is reactions involving carbocations. You're going to see these a lot more. And so when we're thinking about this, the way this reaction is going to proceed, right? We want to go from areas of high electron density to low electron density. So it'll do like that. Now we're left with a dilemma, right? We're essentially taking this double bond and we're breaking it down into a single bond. And we're taking those two electrons and we're going to form a bond with hydrogen. Now the hydrogen can be added into two places, right? We could add the hydrogen right here, right, and leave a carbocation right there. Or we could add the hydrogen onto the opposite side and leave a carbocation on this side and have the hydrogen right here. Right? Does everyone kind of agree with that so far? In terms of this would be the general reaction mechanism for this particular reaction. Yes, no, maybe so. Okay, I'm gonna take the silence as a yes. Okay, so from those two possible intermediates, right, that bromine can come back in. It's now gonna have a -1 charge. And there's two places where it could attack based on what the actual molecule was. It could attack at this carbocation, or if the carbocation was formed at this carbon, it would attack here. And so then your products would end up looking like this. Right? And so these are the two possible products, right? So there's one thing about this though. It actually ends up being that this is the kind of predominant product and we get none of this. And so kind of the next question is, why are we getting none of this secondary product, right? We said that this is a possible thing that could happen. And so let's think about, what kind of carbocation is forming here. So in this pathway, we have a tertiary carbocation forming. And in this pathway, we have a primary carbocation forming, right? And so from what we've learned, we know that primary carbocations are the least stable. So it makes sense why we have none of this product forming, right? It's forming through a primary carbocation intermediate, which is going to be not as favorable as having this tertiary carbocation intermediate. So now let's kind of go through and explain why, this ordering of tertiary carbocations being more stable than secondary, being more stable than primary is occurring. And so to kind of think about this, right, this is essentially just a reiteration of the previous slide. And we just have a tertiary carbocation here and a primary carbocation right there. And there's about a 115 kilojoule per mole difference in the heat of formation for these two carbocations, which leaves about 78 kilojoules per mole of extra stability by having more alkyl groups. And so the way that we're going to explain kind of this stability that is brought on by having alkyl groups is through this topic of hyperconjugation. And so in thinking about hyperconjugation, what that really is going to mean is kind of this idea of the carbon's ability to gain electrons through almost kind of this weird inductive effect. And so let's just draw in a carbon like this, right? And let's say that there's going to be CHs right here. Yeah. And let's put a hydrogen right there, right? And so this would just be a secondary carbocation, right? And so to think about hyperconjugation, let's draw in these hybridized orbitals on these carbons. And so the way that we're going to think about that is we know that there's going to be these sp3 hybridized orbitals. Gosh, okay. Kind of like that. And let's put a hydrogen right there. And to simplify this drawing, I'm just going to do this. And let me just do that for this one as well. So these are what the kind of the hybridized orbitals are going to look like on these carbons, right? And so the way hyperconjugation works, and the reason why having more alkyl groups stabilizes a carbocation, is because in this shared bond between this carbon and the hydrogen, they allow overlap of this bond and this bond. So that way, this MTP orbital of this carbocation feels some of the electron density in this sp3 hybridized orbital. So it's like the more things, the more carbon-based groups you have around you, the more they're able to share their electron density a bit and help stabilize the carbocation. Does that make sense? Are there any questions on that? This idea of hyperconjugation is super important and is going to be kind of the reason why we think about carbocations in the way we do, and why, you know, having a tertiary carbocation where you have 3 carbon-based things around you that are able to share their electron density is better than just having one. Okay. And just as kind of another interesting idea that we won't get into, but one thing to note is that these bonds have to be parallel or in the same plane as this p orbital. And this is going to come back later when you're thinking about like vanillic carbocations. So where you have a carbocation and it's part of a double bond or triple bond. And this one, just as a spoiler alert, is going to be the least stable carbocation. So we know, I know we've talked about how primary carbocations are like super unstable. Well, this one is even more unstable than a primary carbocation. And the reason why is because there's no orbital overlap between those adjacent alkyl groups. And if you want to learn more about it, please stay after lecture and we can talk about it. Cool. Okay. So yeah, this is kind of just a summary. Yeah, that's how that word goes. So in order to stabilize carbocations, molecules can undergo changes known as hydride and methyl shifts that bring forth a more stable carbocation. And so this is kind of just a sub idea in stabilizing carbocations. And so when we think about hydride and methyl shifts, let's just flash forward to that. All that means is that we're able to make a more stable carbocation from something that's less stable, or we're able to make a carbocation that's just as stable. And kind of the idea here is in hydride, right, we're moving a hydrogen, we're shifting it over. Methyl, we're shifting over a methyl group. You can also have like ethyl shifts, but the general idea is you're able to make a more stable carbocation. And the way that this works is, imagine you have this secondary carbocation right here, right? It's a carbon and it's connected to alkyl groups, secondary. Now, what if we took this hydrogen and it shifted over like that? And so now it's connected right here. Well, when we do that, what happens to the positive charge is it moves over to this carbon. And notice what you've now formed. You've now formed a carbon with a positive charge that has 3 alkyl groups attached to it. So now we're at a tertiary carbocation. So now we've gone from something that's not as stable to something that's like super stable, right? A tertiary carbocation. You can do the same thing with this methyl group here, right? If you took this methyl and you just shifted it over, right, the methyl groups end up here. And now you've gone from a secondary carbocation to another secondary carbocation, right? They're in the same energy, but these are going to be both equally favorable structures. And so these are going to be really important to watch out for, especially when you get into more reactions where things can be shifting around, and is going to be a driving factor of having kind of reactions where you can form multiple different products. So are there any questions on kind of what I just went over about carbocations and hydride shifts and methyl shifts?
I have a quick question. If in the methyl shift, it results in an equally favorable conformation, then why does it even shift in the first place?
It's just because it can happen, right? In thermodynamics, things are moving around all the time. And as long as this thing isn't at the same energy level, right, based on the energy diagram, it's just the thing that's going to happen. It's kind of like when you think about Brownian motion, right? And you have molecules just moving around and shifting and vibrating, right? If something can happen, it will happen. Does that answer your question? It's like it's just an orgo, let's see what happens kind of thing.
Okay, yeah, thank you.
Yeah. Okay. What other questions are there?
So my understanding of hyperconjugation so far is that because the bonds are in like close proximity to each other, they can kind of share their electrons.
Yeah.
But up until now, it seemed like overlap of electrons is a bad thing. Like in Newman projections, we always want to avoid that. So why is it like good to have them close together in carbocations as opposed to like in Newman where we would prefer the staggered to the eclipsed?
Yeah. So the key part or the key aspect of this is that we're not overlapping electrons, we're overlapping hybrid orbitals. And so when you have this carbon with a plus charge, right, that means it's electron deficient. And let me just draw this p orbital a bit better, right? It has that positive charge because it's missing electrons in that p orbital. And so when you're able to overlap here, what you're doing is you're allowing the electrons that rest between this carbon and this hydrogen, you're allowing them to be kind of shared here. It's just this idea of distributing electrons and adding them to a place where they originally weren't, where there was a positive charge. By having these electrons nearby, you can kind of move it into this place. It's like having, you know, a waterfall essentially, right? You have water going from a really high place to a place that's lower in energy. So in Newman projections, you were thinking about, you know, orbitals that already had electrons. So this would have had electrons and this would have had electrons. In hyperconjugation, this doesn't have any electrons. Does that answer your question?
Right. So the reason that more alkyl groups are more stable is because they're just more electrons that the deficient carbocation can like pull in to itself, basically.
Yeah, exactly. That's spot on.
Okay. All right.
Cool. Okay, I'll now turn it over to Ashley to continue our lecture.
Let me share my screen.
Okay, so today I'm going to be talking about acid-base stability. Oh, let me erase that. Before I go into new topics, I kind of just want to review the definition, Bronsted-Lowry definition of acids and bases. So an acid is something that donates a proton, right? And a base is something that accepts a proton. So if we look at this reaction right here, we have a base. This base is going to form a bond with this H and receive or accept this H, right? So it's going to form a bond. We know that this H right here can only have one bond. So this bond right here between this O and H is going to break, and these electrons are going to go to the oxygen. And I just want to review, although you guys might know this already, that when this acid loses the H, right, or gives off the H, it now becomes a negative, right, because it receives those electrons. But this becomes a base, right, but more specifically the conjugate base, right? So this molecule right here, this base, is the conjugate base of this acid. And this is going to be important for something we're going to talk about in a moment. But now let's look at the base, this one as well. This one gained the H, right? So now it has a positive charge, and this H right here. And this became an acid, or more specifically, it became a conjugate acid. That's supposed to say conjugate. So we're going to be focusing on conjugate and how conjugate affects like the stability of acids and bases, or when we're ranking acid bases, how that's important. Let me go ahead and erase that. Okay, so sometimes it's important, let's say you have a list of acids and bases, it's important to know which one's stronger or which one's weaker, right? Because when an acid is stronger, it's more able to give out an H, or when a base is stronger, it's more able to like want the H and receive the H. So they're kind of more reactive, right? That's the way to think about it. So it's important to know which ones are more reactive, right? So the best way to like rank acids and bases is to look at the conjugate of that acid and base, right? So when we're looking at the conjugate, whenever the conjugate is more stable, that's going to mean that the acid or the base is stronger. So for instance, what I mean by that is that we had looked at this equation at the bottom. We're going to focus on the acid right now. We said that this is the conjugate base right here. Whenever this conjugate base right here is more stable as compared, let's say we're comparing two different acids, right? If this base is more stable than the other conjugate base that we're looking at, then this acid right here is the stronger acid, right? And that sort of makes sense, right? Because let's say we're looking at this acid and this conjugate is more stable, then this acid should want to lose the H to become this molecule right here because this is more stable, right? So this is more favorable. So that's how we're going to be looking at this when we're comparing acids and bases, when we're ranking them. We're going to be looking at what forms a more stable conjugate, right? Whether we're talking about base or acid. Is there any questions so far? Okay, so some factors that affect stability of acids and bases are going to be charge, elemental effects such as electronegativity and the size of the atom or the radius of the atom, polar inductive effect, which we'll talk about if you don't know what that means, and then resonance as well. So let's go into, first we're going to focus on acid stability, and then once we go acid stability, we'll go into base stability. So let's first look at charge and how charge affects the stability of the conjugate and how that affects acidity. So first, we're gonna again focus on charge. The lesser the charge that the conjugate has, or in other words, the lower the charge density on that conjugate base, the more stable it is. And again, just to reiterate what I said, more stable conjugate equals more acidic or basic. In this case, we're talking about conjugate base. And it's going to equal more acidic or acidic molecule. I said the same thing, but you know what I mean. So for instance, this example right here, we're ranking the following molecules from weakest to strongest to weakest acids, with 1 being the strongest and 3 being the weakest. So our first step, right, this is our acids, should be to draw the conjugate bases. So we're going to draw the conjugate of this water. Essentially, the conjugate base is just whenever a base comes in, takes a proton. This electrons go here. So now you have OH. Let's do the same for this one. This is just H2O. This becomes O2 minus. There you go. So you were just essentially removing an H, those electrons from the bond are going to the oxygen. So that's how I got to these. So now we're looking at the conjugate base. And again, we're looking at how less charge or lower charge density on the conjugate base makes it more stable. More stable conjugate base, right? We're focusing on the conjugate base, is a stronger acid, right? So in this case, does anyone want to say which one has, or which one is, in the case of the conjugate base, more stable?
The middle molecule, the one that forms
Right.
water.
Yeah, so this molecule right here, this one, H2O, yeah, you're correct. This one has lesser charge, right? This one has a negative charge versus this one that has O2. So this one right here has a lesser charge, so it's going to be more stable. And therefore, because the conjugate is more stable, then this acid right here is going to be stronger as compared to the other one. So we're going to number this at number 1, right? And then this one over here has less of a charge than this one. So we're going to go ahead and number that number 2. And then this one at number 3. Right, and just to focus on this one right now, it makes sense that this one is the least stable, right? So this conjugate base is least stable because you have a lot of charge in one molecule, and we know that charges repulse, right? So we want to kind of be able to delocalize those electrons because delocalizing is more stable. So if you have them all in one spot, that is not very stable, right? So more, like we said, more stable is a stronger, more stable conjugate base is a stronger acid. If it's less stable, it's like a sorry, I lost my train of thought. If it's less stable, then it's going to be the opposite of what we said, right? So in this case, it's going to be a weaker acid because this molecule right here is not very stable. Did that make sense? I hope I didn't confuse anyone. Are there any questions on this? Okay. So next, so this is just the answer, so you guys can look at it later. Another way you can think about charge and how it affects acidity is that usually in Gen Chem, right, when you looked at a positive charge, it was, or like a molecule had a positive charge, it was usually an acid, right? So a way to think about it is if a molecule is positively charged, it's most likely an acid, especially if it has the H in the formula. So for instance, if we look at this one, it has a positive charge, has H's in the formula. We know that if this molecule were to lose this H, it would be neutral, right? And we know lesser charge is better. So we can also figure out that this is very acidic. And also this is just H3O plus, which you guys know is an acid. So if you look at positively charged, more likely it's going to be an acid. Okay. So next we're going to talk about elemental effects and how they affect acidity. There's 2 types of elemental effects that we're going to be focusing on. We're going to be focusing on electronegativity and then the radius of the atom or the size of the atom, right? So let's focus first on electronegativity. When we're comparing different types of acids, right, or comparing those atoms, then if they're in the same row like this, right, the more electronegative the atom that is donating those electrons, the weaker the conjugate base, or the more acidic. So essentially what that means is that as you go to the right of the periodic table, it's more electronegative, but also that means that it's increasing in acidity. So now let's focus on the radius of the atom or the size, right? So we're comparing different acids when we're looking at the conjugate base, right? If we're comparing them and they're in the same group, going like up and down the periodic table like this, the larger the atom size, right, the weaker the conjugate base or more acidic. So essentially, in other words, size increases as you go down the periodic table, and so does acidity. Okay, so let's do an example together. Rank the following molecules from strongest to weakest acid, 1 being the strongest, 3 the weakest. So we have our acids here. So what should be the first step we do in order to figure out which one's more acidic or which is more or weakest acid? What is the first step we do? Well, what we were talking about on the last slide, we're talking about something that starts with the C. What should we draw first?
The conjugate bases?
Yeah, so we should draw the conjugate bases of these acids. So these are just going to be Br minus, I minus, Cl minus, right? So these are the conjugate bases. And then look at, where they are on the periodic table. So let's look at Cl, Br, and I, right? So they're going up and down the periodic table. So we would use this row right here, right? That as the atom gets larger, acidity increases. So essentially, as you go down the periodic table, acidity increases because radius does too. So then we would, doing that, which one do you guys think is more acidic?
HI.
Yeah, HI would be more acidic. So this one would be your number 1. And then the next one would be Br, and then HCl, like that. And that also, if we think about it, that makes sense, right? So we talked about how electrons, repulse, they don't want to be that close together. That's unfavorable. So they have more space where they can delocalize, that is more stable, right? So we look at, for instance, HCl versus I minus, right? I has a larger radius where electrons can delocalize. So it makes sense that the conjugate I minus is more stable. And because the conjugate is more stable, then HI, the acid itself, is stronger. Does that make sense so far? Is there any questions? Okay. So let's move on. So the next factor that affects acidity is polar substituent effect or polar inductive effect, right? These two mean the same thing, can be either or. In this case, we're going to be focusing on substituents, right, that are electronegative, right? And essentially, it's called polar substituent effect because they're they're gonna kind of polarize the molecule. So that's why it's polar substituent effect. So we're going to focus on electronegative atoms, right? So the presence of electronegative atoms increase the acidity by inducing electron density towards itself. So what do I mean by that, right? What does this mean? So for instance, if we look at this molecule right here, we have an electronegative atom right here, Cl. This electronegative atom, we know that electronegativity means that it wants electrons. It's going to pull electrons towards itself. So it's going to be like a partial negative, right? Because it's going to draw electrons towards it. And as a result, what it's going to do is that it's going to form a partial positive on these carbons right here, right? So then what happens is that when this molecule reacts, again, we're looking at conjugate base. Down real quick, and let me draw it real quick as well. When we're looking at the conjugate, it's a minus, right? Hopefully I didn't draw more than one. I didn't draw this wrong, but it's a minus because the H was removed, right? So this is the conjugate base. So the reason why this is important, right, because we have partial positive and this is partially negative, is that this partial positive is going to stabilize this negative charge, right? And we said the stabilization of the conjugate base is going to increase acidity, right? So the reason why it stabilizes it is because if there's partial positive, is going to share some of those electrons, right? And then kind of make it less strongly negative, right? So it's going to be less reactive, so it's more stable. So again, more stable, more acidic. Is there any questions so far? Okay. So presence of electronegative atoms, what they do, they induce electron density towards itself and then stabilize the charge once the molecule reacts, right? And we know that stabilized conjugate base is more acidic. Just to add to that, when there are more of these electronegative atoms, such as more CLs, such as right here, that's going to increase the effect, right? So it's going to more strongly stabilize the oxygen, as well as when the Cl is stronger, right? So this versus this Cl is stronger to this H that can be lost. So this has a stronger effect on stabilizing that charge as compared to this one, right? So now that I've mentioned that, if we do this example, right, we're ranking the molecules again from strongest to weakest, where 1 is the strongest and 3 is the weakest. Which of these is going to be the strongest acid? Does anyone have any questions? Okay, so let's work it out together then. Okay, somebody answered, yeah. So somebody said this one is going to be more acidic right here. And that makes sense, right? Because we said when you add more electronegative groups, right, it's going to increase kind of the partial positive here, or increase that effect, so that when you draw the conjugate base, right, the conjugate base has a negative charge, it's going to stabilize the negative charge more stable conjugate base is more acidic, right? So this is going to be number 1. That should be a 1. Looks like a 2. Let me redraw that. There we go. And then the next one would be this one, right? And then this one. So the reason why, we compare these two, this one is farther away, and we said when CO is closer to this molecule right here, it's going to have a higher effect. The CO is closer to this one, so it has a higher effect. This versus this, again, this one has less electronegative groups. This one has more, so this one would be more stabilized, so that one's a stronger acid. Does that make sense? Is there any questions? Yeah, I can draw the conjugate for this one. So that's the conjugate for this one, right? These right here, right, are going to pull electron density towards them. So they're going to make these partially positive. These carbons are partially positive, right? More than if you only have one of those electronegative molecules. So this negative right here is going to be stabilized more than if we only had one Cl. Does that make sense? Okay.
So if on the far right molecule, not the conjugate, but the strongest acidic one, if that's chlorine and hydrogen were switched,
These two?
the one on the left,
This one?
the chlorine on the left.
This one?
Yeah. If
Okay.
that and the hydrogen were switched, the hydrogen below the carbon, would that result in a stronger acid than the one right there?
No, it would be the same. It doesn't matter where it is localized in terms of this carbon. It just matters which carbon is attached to. Like in terms of this carbon is a lot farther, right? But this one's closer. But I don't think it matters if these are switched.
Okay, thank you.
Yeah. Is there any other questions? Okay. So that's the answer to that. And lastly, when we're talking about acidity, another thing that stabilizes these molecules is resonance. So we're looking at resonance, right? So resonance, again, we talked about how having electrons just in one space it's more favorable to delocalize electron density into more places, right, or more locations. In this case, resonance is a delocalization of electron density to different atoms, right? And that makes the molecule more stable. So if it's more stable, again, it's a stronger acid. And there's an example right here where first, if we focus on this one right here, this loses its H, right? And there's no resonance versus this one right here, if it loses its H, right? Because it's an acid. Then in this case, there is resonance. And let's zoom in just to draw that in here, right? So there's electrons here. These electrons can go here. And then this bond is gonna, or those electrons in those bonds are gonna go to this oxygen. And now this oxygen over here has that negative charge. So that negative charge is being delocalized onto oxygens, right? So there is more stabilization, or in other words, resonance stabilization in this molecule right here as compared to this one. So if we look at the acid or the pKa, sorry, this pKa value is much lower as compared to this one. So this is more acidic. So when molecules have resonance, they're more stable, right? So when we're looking at conjugate bases, if it has a resonance, it's going to be more stable. Is there any questions on that? Okay. So now, since I talked about acid stability, I'm going to go through very quickly on base stability because it's just the exact opposite of acid stability. So when we're ranking bases, we're still looking at the conjugate, right? Except when we're looking at the factors that affect base, those factors are going to get affect the base opposite of acids, right? So when we're looking at the elemental effects, we said that for acid, acidity increased as you go to the right of the periodic table and down, or in other words, just like this. But when it comes to bases, basicity also actually increases as you go to the left and up. So in other words, like this. So it's just going to be the exact opposite of acids. And the charged effect, we talked about how less charge is better. That also applies here. And again, usually negative charged molecules are usually basic. And then when we're talking about the polar effect, right here, the presence of electronegative atoms actually decrease basicity, so the opposite effect. In the other one, it increased acidity. In this case, it decreases basicity. And I'm just going to do a very simple example on that. Just zoom in here. So I'm going to do a very simple example. Sorry, this is bases, so it's going to have a minus charge versus something that looks like this, right? So if we had talked about how electronegative atoms like Cl, they pull electron density towards themselves as a partially negative charge, and they create, let me redraw this bond right here. They create partially positive charges, right? So let me draw those, partially positive, partially positive. We talked about how these partially positive stabilize the negative charges, right? So there's stabilization happening right here. So when we're talking about bases, right, you can see that this base is being stabilized. So we talked about how stabilization, it's usually, well, maybe I didn't mention this, but stabilization usually means a weaker acid or weaker base. So when we're looking at this directly, this is going to be weaker, a weaker base. Okay. because it's more stabilized, versus this one that does not have that stabilization, right? So this is not going to be as weak as this one. So when you add electronegative atoms such as Cl, it's going to weaken the bases. So the opposite of what we talked about with acids. Is there any questions on this? Okay. So that is acids and bases. Now we're going to move on into a different topic of boiling points. And I'm going to try to go through this very quickly because we have 7 minutes. So when we're looking at molecules, sometimes we want to rank them based on boiling points, like which one has a higher boiling point versus lower boiling point. So when we're ranking boiling points, there's 3 important factors that we want to look at. The first factor would be intermolecular forces. The second factor would be number of carbons. Number of carbons correlated to molecular weight, right? As the number of carbons increases in a molecule, the molecular weight also increases. And we're also going to look at branches. So we're going to talk about each of these points in a minute. But first, I just kind of want to review the 4 intermolecular forces, which you guys might be familiar with, but I'll just do it very quickly. So ionic forces, right, are electrostatic interactions between oppositely charged ions. So in this molecule right here, you have Na plus and CO minus. This is an example of an ionic interaction, right? We also have hydrogen bonds, which are interactions that involve hydrogens, and also like a molecule that has high affinity for electrons, such as fluorine, oxygen, and nitrogen. An example would be this right here. Let me kind of zoom into that. There's interaction between oxygen and hydrogen, right? That's an example of hydrogen bonding, right? And then we also have dipole-dipole, is when there's partial charges, right? And those partial charges, there's a partially positive, partially negative. Those 2 charges are attracted to each other. So this can also be an example of that. Let me just zoom in. The oxygen has a partially negative charge, as you can see right here, while the hydrogen have a partially positive charge. So there's going to be interactions, right, between attractive interactions between this negative, partially negative charge and partially positive charge right here. And last, we have van der Waals dispersion forces. So let's zoom into this one. Essentially what that is are temporary fluctuating dipoles. So if you look at an atom, we know they have electron clouds around them like this. Sometimes those charges kind of fluctuate into one side directly, such as there is this temporary dipole where this is partially negative and partially positive. I know my partial sign is horrible, but that's what it means. And then these interactions right here are van der Waals dispersion forces. So it's just when there's temporary fluctuating dipoles, that's what it means. Is there any questions so far? Or on any of these definitions? So now let's go into each of them. Okay, so first we're going to talk about intermolecular forces. So when we're looking at intermolecular forces, right, ionic forces are stronger, right, because they're, so, and like for instance, Na plus and CO minus, right, those are actual charges. Well, all of these are talking about either partial charges or just interactions that don't involve charges, right? So ionic forces are going to be stronger than hydrogen bonding is going to be stronger than dipole-dipole and then van der Waals, right? Does anyone have any questions on why this is the way it is? Okay, so now how does this affect boiling points, right? So because this is a stronger interaction as compared to van der Waals, whenever a molecule has this type of interaction, the boiling point is going to be higher. right? Because if they have, so if we're comparing boiling points of molecules, if those molecules have stronger interactions, they're going to be harder to pull apart, right? And boiling point is essentially kind of when you pull those molecules apart and it kind of evaporates, right? So whenever it's stronger, it's going to be harder to, or it's going to have a higher boiling point, in other words. So if you look at this graph right here, ionic molecule, such as this one right here, has a higher boiling point as compared to a dipole-dipole because it's much weaker. Right, so ionics are going to be, ionic forces are going to have a higher boiling point. Is there any questions on this? Sorry if I'm rushing. I have like 2 minutes. Okay, let's go to the next one. The next thing to focus on is carbon chain length. Again, I said that carbon chain length, or the size or the length of the chain, is correlated with molecular weight, right? As you increase the chain, you increase the molecular weight. So boiling point increases with molecular weight. So in other words, the longer the chain, the higher the boiling point. This is right here. So why is that the case? So let me draw an example right here. Versus, I know that is wonky, right? So the reason why that is because when you have a longer chain like this as compared to this, there's more surface area for these chains to interact. And when they interact, you open the possibility of them having van der Waals interaction. So this has more van der Waals interactions than this. And we talked about how van der Waals interactions are able to increase the boiling point, right? So if you look at this line right here, this one has a higher boiling point than this one right here. And it's because it has a higher surface area, you're able to have more van der Waals interactions. And it's the same for these. And I just want to quickly point out how when you compare these between these two, right? So this is an alcohol versus an alkene. So they're different functional groups, right? Different functional groups have different possible interactions. For instance, this alcohol right here, you're able to hydrogen bond to something else, right? And we know that also H bonding is a higher force, right, than van der Waals, which is what alkenes have. So therefore, anything that has H bonding, such as these alcohols, are going to have higher boiling point. So you can see that all of these, right, if you compare them to each other, that have the same like kind of chain length. So these have relatively the same chain length. This has a higher boiling point. Okay, so let's move on to the next part. Last but not least, molecular branching. So boiling point increases with increasing branches. So what that means is, for instance, this example right here, if we compare these two, this one right here has more branching, right? And the reason that boiling point decreases with branching is because there's decreased surface area, so decreased possibility for van der Waals interactions. Okay, and then just to quickly add the second point, when you increase branching, you decrease the access to functional groups. And I said functional groups are how molecules interact, such as like this one, hydrogen bonds, right? So there's less availability of space down here for a hydrogen bond as opposed to this one right here, if you look all around. So in this case, when you increase branches, there's decreased van der Waals interactions and decreased access to the polar functional groups. Is there any questions on this? I know we're a little bit over time, so I'm trying to do this quickly. Okay, so this is a practice problem, which I'm not going to go through. So this is the end of the lecture. If anyone has any questions, you guys can stay. We're going to post a supplemental video for boiling points that will go into more in depth and more practice problems that Coral did last summer. So you guys can feel free to watch that. But yeah, if there's no more questions, you guys are free to go. We'll stay here for a few minutes.
Thank you.
Thank you.